মা একটু চুপ দাও। Okay, so yeah, screen is visible, right? Visible.
It's not clear, sir.
Voice is not clear.
The screen is little blur.
Not clear. Okay. Now it's visible.
Yes, sir.
Okay. So today we will start enolate chemistry. Okay. So yeah, write down enolates. So enolates means, uh, first of all, this this in actually comes from your double bond. Okay, this in term is actually coming from your double bond. And this all means you have alcohol. So in stands for double bond, all stands for your alcohol, and this 8 stands for anion. This 8 term stands for anion. So basically what we have a double bond, we have alcohol, and we have anion. So this is your enolate thing. So how can you produce the enolate? So suppose I have this ketone compound RC double bond O CH3, right? So if I use some base here, okay, if I use some base, so what will happen? The base will abstract the proton, right? Base will abstract the proton from here. So base is abstracting the proton. What I am getting? I am getting R. Here I have C double bond O, and here you have CH2 minus. So this is the carbon ion you are getting, but this CH2 minus is in conjugation with this double bond O. So this will break. Okay, this will come and that will break. So what I am getting? I am getting one resonating structure like this. So RC, here you have double bond CH2, and this is becoming what? This is becoming O minus. Okay, so this is basically your enolate. Enolate means this carbon ion is in conjugation with a carbonyl group, and after that you are getting this. Okay, so basically this. Now the next thing is, suppose I have this compound double bond O, here I have CH3 and here I am giving some base. So what can happen from here? What are the possible products here? So the base can abstract the proton from this right hand side. I am marking it as your Ha. Okay, and the base also can abstract the proton from this position also, which is your Hb. Okay, so base can abstract this proton also, Ha and Hb. So if it is abstracting this Ha proton, that time what I will get? What I will get? So what you will get? You will get a negative charge here, right? And here you have double bond O, right? If I show it, the resonance, if I show, so negative charge is in conjugation, what I will get? Write down the resonating structure, what you are getting. So here you have CH3, double bond you are getting here, and here you have O minus. Okay, that thing you are getting. Another what can happen? So suppose the base is abstracting this proton, Ha proton, that time you are getting that product. Okay, now if the base abstracts this proton, this Hb proton, that time what you will get? That time what you will get? So here you will get a double bond, okay. Here you will get O minus CH3, right? Clear? We are getting two kinds of products. This thing is clear, right? Clear? Am I audible? Am I audible?
Yes, sir.
Audible, right? Yeah. So we are getting two kinds of products. So this one is what? This one is actually what? This is your more substituted. If you see, so you have one CH3, here you have one bond, here you have one bond. So this is your tri substituted, or I can say this is your more substituted. Okay, more substituted. Okay, and if it is more substituted, so that means what? This is your, that is your thermodynamic product. Okay, this one is becoming what? Thermodynamic product. And if the proton is abstracting from this side, which is actually your less sterically hindered, or I can say this is what, 1 2. So this is basically your less substituted, or you can say di substituted. So this less substituted product, okay, less substituted. So if you are getting less substituted product, so that is actually your kinetically controlled product. Okay, or you can just write down that this is your kinetic product. Okay, so which one is your more substituted? That will be your thermodynamic product. Which one is your less substituted? That will be your kinetic product. This thing is clear. So we are getting two kinds of enolates. Okay, we are getting two kinds of enolates. One is your more substituted or thermodynamic product, another one is your less substituted or kinetic product. This thing is clear. Clear?
Yes, sir.
Clear, right? Fine. So now I am showing you the graph basically. So if you are writing in the notebook, so you just mention here only that below that side, suppose here this side you are plotting reaction coordinate. I am not writing, or you can write down. Okay, this is your reaction coordinate, and here you will plot energy. Okay, so if you plot this and you are getting thermodynamic product, so thermodynamic product means what? You will get a graph like this. Okay, you will get a graph like this. So this is what? Here this is your reactant and this is your product. Okay, so that means what it signifies? It signifies that the product is more stable than your reactant. How to remember? See, product, if you see the energy value, so product has less energy than your reactant. So that means what? Less energy, so that means more stable. Okay, so product is actually becoming more stable than reactant, and that means you are getting thermodynamic product. Okay, so this will be the graph for your thermodynamic product or most substituted product. And this value is what? This is what?
Activation energy.
Activation energy. So this is your activation energy, EA. Okay, this is your activation energy. And if I draw for your kinetic product, okay, so kinetic product means same thing. You just write down here reaction coordinate, and here you plot energy, but one thing is different here. So here the product is less stable than your reactant. Okay, product is less stable than your reactant, and activation energy is this is your activation energy. Okay, so this is your activation energy, and product is actually less stable than your reactant. Okay, so that is the thing. So if you are getting thermodynamic product, if you are getting thermodynamic product, that time you will get what? You will get this kind of plot. If you are getting kinetic product, so that time you will get this kind of plot. That is the thing. Okay, fine. So now just write down মা মা কি কইব ক্লাসটা শুরু করলো নাচ শুরু করে দিল Okay, sorry. So here write down that write down here thermodynamic enolate, and another one is your kinetic enolate. So we have two kinds of things, thermodynamic enolate and kinetic enolate. Okay, so it depends basically on the nature of the base. So first of all, just see which kind of base we are using here. Okay, so in thermodynamic enolate we are using base, means this will be your weak base. Okay, weak base, or I can say this is your inorganic base. Okay, inorganic base. So these are the two kinds of base we have, weak base or inorganic base. So that means what? That means we have NaOH, okay, inorganic base, you know, KOH, okay, sodium hydroxide, potassium hydroxide, even you have NaOH, okay, even you have what? Uh, Potassium tertiary butoxide, okay, potassium tertiary butoxide. So these are all the your weak base or inorganic base. If you are getting this kind of inorganic base or weak base, so the chances there you will get your thermodynamic enolate. Okay, and kinetic enolate, so that time you will get which kind of base? So it will be a strong and hindered organic base. Okay, strong and hindered, strong and hindered organic base. So for example you will get LDA, you know, lithium diisopropyl amide. Okay, suppose you have this LiHMDS. Okay, even suppose you have this pH3C minus. Okay, so this kinds of bulky base, if you are getting this kind of sterically hindered and bulky base, that time there is a huge chance that you will get kinetically controlled enolate. Okay, so that is the first differentiate you can do. One thing is your inorganic base and the second is your bulky organic base. Okay, number 2 point, and that is also important. Number 2 point is your temperature. Okay, temperature, it actually plays a crucial role, this temperature, because when you will do in practical, that time you will know that this temperature actually plays a very crucial role. So if you have high temperature, okay, if you are providing high temperature means generally the temperature which is greater than your room temperature. Okay, the temperature which is greater than room temperature, greater than 25 degree centigrade. So if you are providing 30 degree, 40 degree, okay, 50 degree, that is your basically high temperature. So high temperature favors your thermodynamic enolate, and here low temperature, if you have kinetic enolate, that time you have to provide low temperature. Now suppose I am using one bulky base. Okay, I am using one bulky base. So suppose I am using this pH3C minus sodium plus, right? So this is a bulky base, and here I am maintaining the temperature minus 78 degree centigrade, which is a very low temperature. Okay, so if you maintain a very low temperature with a bulky base, that definitely provides you a kinetically controlled enolate. But suppose the same base, that bulky base I am using, but temperature I am changing. Okay, temperature I am changing, here I am maintaining 35 degree centigrade. Okay, so that time it will show you what? Thermodynamic enolate. Okay, because if you increase the temperature, that time automatically what? The activation energy will low. Okay, because their kinetic energy will increase, you know, the collision between the molecules will increase. Okay, and that is the reason if you provide higher temperature you will get thermodynamic enolate. But if you do this lower temperature, so that means your molecules are almost freeze. Okay, molecules cannot collide with each other. If you provide that much low temperature, molecules are almost freeze. Okay, they cannot do that much collision, and that's why you are getting this kinetic enolate. Okay, and another point, that cyclization reactions, all types of cyclization reactions, write down that all cyclization, all cyclization reactions, all cyclization reactions are thermodynamically controlled. Okay, all cyclization reactions are thermodynamically controlled. So anything cyclization reaction is happening, that is your, you will get thermodynamically controlled product. Okay, so only these 3 points is sufficient to remember. Okay. Clear? Am I audible? My voice is breaking, voice is fine today.
Yes, sir. Clear.
Fine, right? Okay. Okay, fine. So next, suppose, yeah, this example we have already seen. So suppose you have this. Okay, here you are using some base, and when you are using some base, we are getting two products, thermodynamic product and what, kinetic product, right? So here you have CH3, here I am getting O minus, and another one will be your kinetically controlled product, so that will be like this. Okay, so this is your thermodynamically controlled product TC, and this is your kinetically controlled product KC. Okay, sometimes in books they write down like this, they will write down like this, TCP, so that means thermodynamically controlled product, KCP, so that means kinetically controlled product. Okay, don't think this is out of syllabus, they just mention like this for short term, shortcut. So now what are the bases we can use? So suppose I am using LDA, and then suppose I have DME, dimethyl ether. DME means what? Dimethyl ether, which is a solvent. Okay, which is a solvent. LDA is the base, and LDA is what? LDA is what? This is what? This is your bulky base, right? So which product you will get as your major, thermodynamic or kinetic?
Kinetic.
Kinetic. So here you will get around 99% of this product, and this percentage, okay. So if I use this bulky base, you will get 99% of this kinetically controlled product, and 1% you will get thermodynamically controlled product. Okay. Now second, suppose I am using this reagent, pH3 C minus sodium plus. Okay, again you are using this solvent dimethyl ether, DME. Okay, sometimes they can ask what is the role of DME. So DME is just a solvent to dissolve the reactant and this substrate. Okay, and if you mention heating here, heating means what? Heating means normally it's a high temperature. Okay, so see, it's a bulky base, this pH3 C minus sodium plus, it's a bulky base, but the temperature is high here. So if you have high temperature, what you will get? You will get thermodynamic enolate as your major product. So that time don't think that okay, we have a bulky base, so we should get kinetically controlled product as a major, but that is not the case. You have to check the temperature as well. If you have high temperature, you will get thermodynamically controlled product as a major. So you will get 90% of that and 10% of this. Okay, now suppose third reagent I am using this potassium tertiary butoxide. Okay, potassium tertiary butoxide, and in presence of tertiary butanol. Okay, and they have not mentioned anything about the temperature. So tell me what you will get. Suppose they have not mentioned anything about the temperature, what you will get?
Thermodynamic product.
Thermodynamic product, because if they are not mentioning anything, and this potassium tertiary butoxide, so potassium tertiary butoxide is what? It's a bulky base, basically it's a bulky base, but the thing it is your inorganic base. Okay, it is your inorganic base. So when you have an inorganic base, you will get as your you will get your thermodynamically controlled product. So you will get 93% of that and 7% of this. Okay, number 4, suppose you have this LiH MDS. Okay, again you have DME, dimethyl ether, Okay, minus 78 degrees centigrade. So if you see this low temperature means you will get kinetically controlled product. So 100% you will get and 0. Okay, it's a bulky base as well as you are getting you are giving low temperature as well, so you will get kinetically controlled product as your measure. Okay, clear. Kaveri, you just see the recording. Okay, we have not done so far, like not that much. So we have two kinds of enolate: thermodynamically enolate and kinetically controlled enolate. Okay, thermodynamically controlled enolate means it will be more substituted, and kinetically controlled enolate means it will be less substituted. Okay. Now, what are the factors you have to remember? So, first thing is base, nature of base. So, if you have weak base or inorganic base like this, you will get thermodynamic enolate. If you have strong, bulky, and hindered organic base like this, LDA, okay, this triphenyl, okay, this kind of thing. So, you will get kinetically controlled base. And second thing is your temperature. If you have high temperature, it will be your thermodynamic enolate. If you have low temperature, that time you will get kinetically controlled product. Now suppose you are using that base LDA, but you are doing the reaction in room temperature or higher temperature, that time also you will get your thermodynamic enolate. So temperature is very crucial. And all kinds of cyclization reactions, what we will do basically, suppose your aldol reaction or Cannizzaro reaction, all types of cyclization reactions, they are thermodynamically controlled. Okay, all the reactions, cyclic reactions are thermodynamically controlled. So based on this, we have this chart. We have like this is the only reactions we have done in lab, but we tried different kinds of reagents. Okay, and based on the nature of the reagents and temperature, we are getting different ratio of the products also. Okay, so this is experimentally
Yes,
done.
sir.
Clear? You just see the
Yes, sir.
you just see the recording, you will get a clear idea. Huh? Okay, now next, suppose you have a Norboran type of system. Okay, so this I have, this thing I have. Now suppose here the first reagent we are trying here, so this is your LDA, then suppose I have THF, and here I have minus 78 degrees centigrade. So that is one. Second thing is what? Second thing is your this NaOET, ethanol. Okay. And third, I am giving you this potassium tertiary butoxide. Okay, potassium tertiary butoxide in potassium tertiary butanol. Okay, so write down the product, try to write down the product, what you are getting. So if you see here also you have two possibility. One is this proton is also acidic. Okay, and you have also proton this side also, both side you have proton. So this base can abstract the proton from here also. So now check where you are getting more substituted or less substituted. Check it. So first of all, tell me this one LDA THF. THF is the solvent tetrahydrofuran and minus 78 degrees. So low temperature bulky base, that will lead to what? Kinetic or thermodynamic? Kinetic or thermodynamic?
Kinetic, sir.
Kinetic product, right? So that will abstract the base from the less sterically hindered side. Okay, so once it abstracts the base, you will get this. Okay, you will get this. Right? This thing you are getting. Right, this is your kinetically controlled product, right? Kinetically controlled product, KCP product. Clear?
Yes, sir.
Clear, right? Now
Yes, sir.
tell me what about these two reagent, NaOET ethanol and potassium tertiary butoxide in tertiary butanol. Now tell me about these two.
It will be kinetic enolate only.
Hmm. So basically here if you see you have inorganic base. If you see the category, which category it falls, NaOH or potassium, this are inorganic, right? So you should get thermodynamic enolate, right? You should get thermodynamically enolate product. So thermodynamically enolate product means, suppose you have potassium tertiary butoxide here. Suppose you have potassium tertiary butoxide, so it will abstract the proton from this side. So you should get this product. You should get this product. Okay, you should get this product because that is the more substituted product. See, 1 2 and this is your 3 try substituted product or most substituted product, but that will not form. Can you tell me what is the reason? Kaveri, can you tell me what is the reason why this
Uh,
compound is
bridging
uh,
bridging double bonds are not non-stable, sir. That's true.
correct,
Correct
correct,
too.
correct, correct. So basically here the double bond is forming on the bridging position. So that means it violates which rule? Braid's rule. Okay, Braid's rule. It violates your Braid's rule. Okay, so you will get the other product, other proton. It will abstract the other proton. So that means what? You will get your this only kinetically controlled product only. Okay, so in all the reagents here actually this type of compound or this type of substrate, they are not depending on the nature of the compound, nature of the reagent, nature of the like temperature. They did not depend on anything. They just depend on the environment of this only. Okay, because bridging double bond is not that much stable, so anything you can use, but you will get this product only, this kinetically controlled product you will get only. Okay, so you can just mention for one line that uh, double bond double bond not stable, double bond not stable, not stable at bridging position, double bond not stable at bridging position. Okay, because it violates your Braid's rule. That is the only thing. Clear? Any doubt? Any doubt?
Yes, sir.
Clear, right? Fine. Okay, so now you will see one by one like how many types of enolates we have, and these are basically important because reactions we will start now. Okay, we will see so many reactions. So first we have write down that lithium enolates. Okay, lithium enolates. Okay, so lithium enolates. So suppose I have this. So here I have double bond O CH3. Same compound I am taking, same compound. Okay, and here I am giving LDA minus 78 degrees centigrade. Okay, one thing I want to mention. Okay, if you want to read this topic from book na, this enolate chemistry, you can follow Claydon. Okay, you can follow Claydon because that is the best book for your enolate chemistry, and it has different versions actually. So I don't know which version you have, so you just go to the index. At the last of the book you will get one index. Okay, index means it is actually your dictionary type. Okay, dictionary type. So here you will get A to Z, like that you will get all the things A to Z. So you just search on E. You just go to E and there you just search for enolate chemistry. Okay, you will get 1 point enolate, and they will mention the page number also. Suppose you will get around 630 or like that. Okay, it varies. Okay, so you just check the page number from there and then you go to your enolate topic. Okay, you will get a clear idea how it is forming. This is a very good book, Claydon, for organic chemistry, and they have mentioned it pretty well. Okay, you will get a clear understanding. If you are interested you can follow, otherwise you just follow notes. Okay, what they are actually what they have actually gave in the book I just written here. Okay, I have taken from there only, but the thing is, yeah, if you are interested you can follow that. But if you do not have that much time, suppose you like For NET exam we have very sufficient time, so you just follow the notes. Okay. But yeah, who will do MSc, that time you have to follow that. Okay, Claydon is a very authentic book and it's a very good book. For inert chemistry, you will get clear idea from there. Okay, so if you have LDN minus 78 degrees centigrade, so which inert you will get, kinetic or thermodynamic?
Kinetic.
Kinetic. So you will get what? This thing, right? This is your kinetic inlet, and this is basically also called lithium enolate. Okay, so lithium enolate means what? Here you will get O minus and here you have lithium plus. Okay, so this is your lithium enolate. Now suppose I am giving here CH3I, so what will happen? Methyl iodide. What can happen? Tell me what can happen now.
Aniline.
Hmm. Aniline.
Not able.
Sorry.
OCH3 will be formed.
OCH3. Why OCH3 will form? So here basically you
Minus
have to
attack.
remember, see here oxygen, so that means it's a hard center. Okay, and if it is in conjugation, suppose O minus is there, if it is attacking by this carbon center, this carbon is basically a soft. Okay, and see what you have iodine. So iodine is actually very less electronegative, huh? Because if you consider with fluorine, chlorine, bromine and this kind of thing, this alkyl halide, these are basically a soft center. Okay, so O minus will only directly attack when you have silicon containing something or phosphorus containing something, that time O minus will directly attack on them. Okay, or suppose some boron containing thing. Okay, that time O minus will directly attack on the silicon center, phosphorus center, boron center. But if you have this kind of carbon center, so keep in mind this carbon carbon bond will form, because this carbon is also soft, this carbon is also soft. Okay, so what will happen, this O minus will back its electron density. Okay, will back its electron density, and this double bond will attack on this carbon center, iodine will leave from here. So this is basically what, this is your SN2 reaction is happening. But the thing is that, okay, which center it will attack, that you have to see. Clear what I am saying?
Yes, sir.
O minus will directly attack only when if you have silicon, phosphorus, boron. So these are basically your hard center. Okay, these are basically your hard center. But if you have this kind of enolate kind of thing, so keep in mind, if you have to form carbon carbon bond, so that means it will always attack from this soft center. Clear? Some pretty clear? Clear? Audible? Am I audible?
Yes, sir.
Audible, right? Okay. Fine. So now suppose next you have this. You have this acetone. Okay, CH3, C double bond O, CH3. Now here I am giving LDA in presence of minus 78 degree centigrade. So this is the first reagent you have. Second you have cyclohexanone. Cyclohexanone structure you know. Cyclohexanone. And third you have this tosyl acid, okay, TSOH in presence of heating. So try to do it. First of all, do LDA, what will happen, do it, because here no need to worry, because both sides you have symmetrical thing. Okay, CH3, and then you just react with cyclohexanone, and this is your tosylic acid in presence of heating. Okay, tosylic acid in presence of heating. So do it, try to do it, then tell me what you are getting. Then you will get compound A, up to this you just do, then we will do further. Indicator about it.
কম্পাউন্ডটা তো প্রথমে এটা তো চিনা হবে, বাকি ওই রিয়েজেন্টগুলো জানি।
রিয়েজেন্টগুলো জানা, এগুলো বড় বড় রিয়েজেন্ট, এটা তো অ্যাসিডন বটে।
এই ট্যাবটা তুমি জানলে কি ওরা দেখতে পাবে? আমি ভাবলাম সেই এটা সেই একটা ট্যাব পাওয়া যায় 120 টাকা, রেখি পরে সাইডে এমনি টিপলে মুছি যাবে।
না ওটা এটা কত টাকা দাম, এটা 3-4 হাজার টাকা দাম মনে হয়। বড় কোম্পানি থেকে আমি মারিয়েছি,
ল্যাপটপটা
ল্যাপটপটা নিয়েছি।
তোমার সুখের চাকরি।
এরকম মনে হচ্ছে রোদে রোদে ধুসে পুড়া হয়ে যাচ্ছে।
CH2 double bond
কথা
COL CH2.
হোয়াট ইউ আর গেটিং?
CH2
হুম
double bond
হুম
C
So basically
OLI
you're
CH2.
saying the first step, yeah. So LDA will abstract the proton from here, because if you have base, so LDA will abstract the proton from here. When it abstracts the proton, what you are getting? You are getting negative charge there, right? So CH2 minus. So if you get negative charge, now that is in resonance. So show the full resonance. Then what you are getting? You are getting enolate, right? CH3 C double bond O, and here you CH3, it will be your O minus, and here you will get double bond CH2. Now the thing is, next step you have cyclohexanon. So if you have cyclohexanon, first of all draw the cyclohexanon. So cyclohexanon means what? This thing, right? So what will happen? You can see you have O minus and you have this is in conjugation, this carbon center. So O minus will back its electron density, okay, and this carbon will attack on this carbonyl carbon, okay, then this bond will break, right? So what will happen? So this is the ring system you have. This double bond O is now becoming what? O minus, and this side you have what? CH2, then you have carbon, double bond O, CH3, okay. See, O minus is back its electron density, so you are getting double bond O, and this double bond breaks now, so your CH2 minus is basically attacking here. Okay, now next what they have given you, tosyl acid and heat. So this tosyl acid is basically a proton source, okay, this is a proton source. So suppose I am giving TSOH, so what will happen? O minus will simply abstract the proton from here, okay. When O minus is abstracting the proton from here, what will happen? You will get here OH, right? And here you have CH2, C double bond O CH3, that is not affecting anything. So you are just getting OH. Now suppose you are adding anything acid, this is because this is also a acid. So if you use one acid, so that means what you have already H plus source, right? Because any kinds of H acid you are using, you have H plus source. So what will happen? Again this OH has a lone pair, so it will abstract the proton, right? Once it abstracts the proton from there, here, so what you are getting? OH2 plus. Now it is becoming a very good leaving group, okay. And what you have here? You have CH2 C double bond O CH3, okay. CH2 C double bond O CH3. Fine. Any doubt? So what can happen next? So next, water is a very good leaving group, so it will leave from here, or you can show like this. Basically, because they have mentioned here, see what they have mentioned, heating. So in presence of heating, this water will leave from here, or you can show like this from here. Hydrogen is coming here and water is leaving, okay. So basically you will get one alpha beta unsaturated system, okay. You will get one alpha beta unsaturated system, alpha beta unsaturated carbonyl compound. Clear? Any doubt?
No, sir.
No, right? Kaveri, any doubt?
No, sir, clear, sir.
No, right? Okay, now do this one. Suppose here I am giving, so you have this alpha beta unsaturated thing. So here I am using this reagent H2O2 in presence of NaOH. Tell me what you will get. and second reagent is your NaN3, sodium azide. Sodium azide. So tell me this thing. If you have this alpha beta unsaturated compound and you are using H2NOH, what can be the product?
Epoxide will form.
So in presence of H2NOH, epoxide will form. Okay, epoxide will form. So here you are getting C double bond O, CH3. So epoxide is forming here. Next, what you have? NaN3. So NaN3 means what? Sodium plus N3 minus. Right. Now tell me, N3 minus will attack in which position? This position or this position? That is the question. N3 minus can attack in which position? Because this is a nucleophile. This is a nucleophile. Okay. So which position it can attack? This or this? Tell me. N3 minus will attack which position? This or this? I am mentioning. This is your number 1. This is your number 2. Which position?
Number one, sir.
1 or 2?
Number one, sir.
1, right? Why? So this number 2 is
Sir.
basically your quaternary center. This number 2 is basically your quaternary. Okay, see how many bonds you have? 1, 2, 3, 4, right? And here this is what? Disubstituted. So if it attacks here, this is actually less sterically hindered. This is more sterically hindered. Okay, so this will open because 3-membered epoxide ring is a strained ring. It wants to release the strain. Okay, so what I am getting here, I am getting this thing. What it is becoming? It is becoming now O minus. Okay, and this side I have what? I have N3 here. Okay, here you have C double bond O, CH3. Now this basically this O O minus, so it will abstract one proton from the solvent. Okay, so ultimately it is becoming OH. That is the thing. Fine. So that is the thing you are getting. Okay, fine, clear. This thing clear? Any doubt?
Yes, sir.
Clear, right? Another question they have given that from this intermediate, if you do ozonolysis of this intermediate, okay, O3 in presence of PPH3, okay,
I have one doubt, sir.
Tell
In
me.
the Na and E3, we are attaching the N3 compound, sir. If it is the O minus, the N3 is also showing the resonance, sir. Is there any possibility to release the N2 gases?
I'm not getting N3 minus is there if you have O minus.
Yes, sir.
O minus
We
means
already have the O minus.
O minus means which O minus?
Sir, in the last product.
This O minus.
This one, sir. Yes, sir. Yes, sir.
Okay, so what you are asking?
Is there any possibility to release the N2 gas, sir?
Okay, so if you see the structure of N3 minus, so it will be basically like this: nitrogen, triple bond nitrogen. So this will be positively charged and this nitrogen will be negatively charged. Okay,
So negative.
now you can show the resonance. So basically you will get this. Okay, so nitrogen double bond nitrogen double bond nitrogen, so that time you will get positive charge here. This one you will get negative charge. Okay, now the thing is, if you want to release nitrogen from here, so that time this is possible, but the thing is the single nitrogen does not exist. Okay, if you have some alkyl group present here, if you have some, suppose alkyl group is attaching with this nitrogen, that time you can, in presence of heating condition, you can release nitrogen because you will get nitrine intermediate. Okay, you will get a nitrogen intermediate. But suppose only you have N3 minus, that time it is not possible to release the nitrogen, because if you release the nitrogen from here na, so you will get a single nitrogen, that is not that stable, right? Single nitrogen is not
Yes,
stable.
sir.
Okay, so nitrogen gas will not release from here, but yeah, if any alkyl group is already attaching with this nitrogen, that time it can release, because you will get nitrogen intermediate. Okay,
Okay, sir.
clear?
Clear, sir.
Okay, now do this. If you do ozonolysis of this compound, so what could be the product? If you do ozonolysis of this compound, what could be the product?
Cyclohexanol.
So ozonolysis means just break the double bond. Okay, then attach one oxygen to this side and one oxygen to this side. So what I am getting, so if I break the double bond, here I am getting double bond O, which is your cyclohexanone. Okay, and here I am getting what? Double bond O, CH3. Okay, and here just attach double bond O. Nothing is there, so that means hydrogen is there, so that will be the product. Okay, so if you do ozonolysis of any alkyl compounds, you just remove the break the double bond, attach one oxygen to this side, another oxygen to this side. Okay, clear?
Clear, sir.
Suppose I am doing ozonolysis of benzene, what you will get? Ozonolysis of benzene, what will be the product? Tell me. Suppose this one I am using in excess, okay, not one equivalent. This ozonolysis, this reagent I am using in excess. So what can be the product? Do it. এটা বল
কি ওটা?
ওজোনলিসিস করেছিস তো?
হ্যাঁ।
কি হবে বল?
PVPH3 কি ওটা?
ওটাই বাদ দে, ওজোনলিসিস তো করেছিস।
মানে ও যুক্ত হয়ে কাটবে তো।
হ্যাঁ, প্রোডাক্ট কি হবে?
বেঞ্জিনে নেটের কইছে
না এটা 11-12 বারে করছি।
এই নেটেরগুলো পাচ্ছে না
করছি ওরা।
এতক্ষণ সময় লাগে? আমাদের টপারগুলোকে দিলে এখনই বললে আমার
বলে দেবে না, ওর একটা প্র্যাকটিস আছে, ওগুলো ভুলে গেছি এরা। 11-12 এর রিঅ্যাকশন ভুলে যায়।
অক্সিজেন করি পরে কাটে মনে হয়, কাটে না? আর ওইটুকুই মনে আছে। লিখি পরে ভাবতে হবে
ল্যাক
এখন পড়াও না আমি ভাবলে ছিল না।
Okay, so what will happen? So you just remove
The
this.
break.
Double bond will break. So attach one oxygen to this side, one oxygen to this side. Then here also you have double bond. So break this double bond. Attach one oxygen to this side, this side. Break this double bond also. So one oxygen to this side, one.
So
oxygen.
your voice is breaking again.
Okay. শেষ হয়ে গেছে কি? আছে নেট দেখ না? নাই।
করে দিচ্ছি,
দাঁড়া আমি করছি।
লোন নিয়ে যাবো।
অন করে দিচ্ছি।
ওইখানে করাই দিলে দিয়ে যাবো।
কি এসে গেছে?
ডাটা ওভার
রিচার্জ লাই প্রত্যেকবার করে
নাম্বারটা সার্চ কর না।
এই তো আছে আমার সিটা। কত বল?
দেখো না কত দিচ্ছি।
21 টাকা না কত বললি?
21
কত আমি জানি না, কত অফারটা কত?
21 হবে মানে 21 1 GB 31 2 GB। কালকে থেকে আর অসুবিধা হয় না, কালকে 1.5 GB থেকে তোমার লাগে না। আমি এমনিতে ফালতু বসে থাকি।
লাস্ট রিচার্জ 22 টাকা দেখাচ্ছে।
তোমার নেটে চলছে না?
জাস্ট ওয়েট ফর 1 মিনিট। হ্যাঁ,
কজন আছে? 2 জন। হ্যাঁ,
বাকি সবাই রেকর্ডিং দেখি। 22 টাকা আছে কি দেখ, রিচার্জটা
আমি করা দিচ্ছি না আমি লোনটা করা দিচ্ছি তুমি লোনটা ক্লিয়ার করে দেবে
লোন কী করে নিবি ওটা?
এয়ারটেল করে দিচ্ছি
রিলায়েন্স থেকে তুই আমি পরে ভরে দিচ্ছি 22 টাকা না 21 টাকা।
টাকা লোন স্টার 500 স্টার 3 আছে লোন হয়ে গেছে পরে ক্লিয়ার করে দেবে
আমি এখনই করে দেবো কাজটা করে। কত টাকা নিলি ওটা?
তো 1 জিবি ডাটা লোন দিয়ে
ঠিক আছে ঠিক আছে, হয়েছে নেট। নাও এম আই অডিবল?
Yes, sir, audible, sir.
Audible? Okay, fine. So what will happen, you just break the double bond, okay, and you just attach. So what basically you are getting, see, if I consider this thing only, so you just make a straight line, then what you have, double bond O here, double bond O here. So this is basically your glyoxal, okay, and you will get 3 equivalent of this, 3 mole of this glyoxal unit, okay. Clear? Voice is fine now, now it is breaking.
I didn't work that, sir.
Yeah, sorry, breaking.
It's clear.
Clear, right? So you have this. Now here also I am giving this reagent LDA, okay, in presence of THF minus 78 degree centigrade. So write down what will be the enolate. So see, if you have base will abstract proton, right? So this side you have sulfur, no proton, this side you have proton. So basically the LDA, okay, LDA will abstract the proton from this side. So what you are getting? You are getting enolate, okay. Which enolate you are getting? So you will get double bond here, O minus here, and here you have S tertiary butyl. This one you are getting, okay. Now suppose you are using here this trimethyl silyl chloride. Now tell me what will be the compound, what will happen? Trimethyl silyl chloride,
Silicon oxygen bond.
silicon oxygen bond will form, right? So basically O minus will directly attack on the silicon center, okay. Chlorine will leave. O minus will attack on the silicon center, chlorine will leave from here. So what is the thing, you write it down. So what you are getting, double bond here you have O Si Me3, okay, O Si Me3, and here you have what is tertiary butyl. This thing you are getting, right? Right.
Yes, sir.
Now suppose you have this tertiary butyl ammonium fluoride, tertiary butyl ammonium fluoride. So what will happen now? What will happen now if you have tertiary butyl ammonium fluoride?
Mine
F minus,
will attack the double bond. OSME3 will leave.
no. So basically if you have silicon oxygen bond, if you have silicon oxygen bond, and suppose you have silicon fluorine bond, okay, silicon oxygen bond and silicon fluorine bond, okay. So which bond is more stronger, which one is more electronegative, oxygen or fluorine? Fluorine, right? So this silicon fluorine bond is actually much more stronger than your silicon oxygen, okay. So if you have F minus, so what will happen, F minus will attack on the silicon center, okay, and this bond breaks, okay. So basically this is a deprotecting reagent, this is a deprotecting reagent, okay, deprotecting reagent of this silicon group. So M minus will attack on the silicon center, this bond will break. What I am getting? Again I am getting this free enolate, okay. So this free enolate again it regenerates, okay. Now suppose I have here cyclopentanone, okay, this is a cyclopentanone. So what will happen? What can happen?
Double bond will attack the carbon.
So O minus will back its electron density. This double bond will attack on the carbonyl carbon. This bond will break. So what I am getting? So first of all, draw this 5-membered ring. Okay. You will get O minus. I am writing directly OH. Okay. And then suppose you have here what? This is your CH2. So this carbon is attaching with this carbon, right? So this, then you have double bond O, and then you have ace tertiary butyl. This thing you are getting. Clear? Any doubt?
Yeah, sure.
Clear, right? Okay, now I am giving one question, try to solve it. Huh? You guys do it by yourself. So 1 2 3 4 5. Do it. Tell me what will be the product. Sound Kumar. What is the product here? Where it will attack? This 1 2 attack or 1 4 attack? Which attack it will do? Am I audible?
Yes, sir.
So where it will attack? 1 2 attack or 1 4 attack?
1 4 attack, sir. Enolate ion.
1 2 or 1 4?
1 4, sir.
1 4, right? Because this negative charge is in conjugation, okay? So this is a soft thing. This oxygen is hard center, but this carbon is your soft center. So if you have soft center, this position is your hard and this position is your soft. So what it will do? It will do your 1 4 attack. Don't attack here, huh? See, in the above cases we have no option. Only this is the electrophilic position, right? That is why this carbon is attacking here. In the above cases we have no option because we have only one electrophilic center. But here we have options, we have a choice between your hard center and soft center. So that is why it will attack on your soft center, okay. And once it attacks here, this double bond will shift to here and this double bond O will break down. So what I am getting, this double bond shifts to here, okay. This double bond O is becoming O minus, okay. Now see what I have. So this you have to attach with here you are getting double bond O, and here you have what is tertiary butyl, okay. Now if you do last step, what they, okay, so they have do protonation H3O plus, so that means hydrolysis of this compound. If you do further hydrolysis, what you will get? So this O minus is becoming now OH, okay, OH. And if you are getting OH, so what you will get? So you will get tautoenol, what? Tautomerism, okay, ketoenol tautomerism.
Ketoenol tautomerism.
Ketoenol tautomerism you will get. So you will get here double bond O, and here also you will get what? Double bond O, here you have S tertiary butyne. Fine. So yeah, these are the things we have. Clear? Any doubt from here? Tell me. Any doubt?
Yes, sir.
Clear, right? Okay.
Clear, sir.
Okay, fine. So second we have silyl anol ether. Silyl anol ether. So if you have silyl anol ether, so first of all write down that silyl anol ether is basically thermodynamically controlled thermodynamically controlled form of enolate. Thermodynamically controlled form of enolate. Okay, thermodynamically controlled form of enolate. Okay, so here we will use different kinds of things. So suppose you have first of all this cyclohexanone derivative, same thing, same compound we are taking. Okay, same compound we are taking, and here we are using different reagent. What is the reagent we have? So we have this Me3SiCl, trimethyl silyl chloride, in presence of triethylamine, Et3N. Okay, Et3N. Okay, so what will happen? So first of all I have written here this is a thermodynamically controlled form of enolate. Okay, so this Et3 triethylamine, it will abstract the proton from here. Okay, this triethylamine will abstract the proton from here, and what I am getting? After proton abstraction, what I am getting? So here I have this ring 6 membered. Okay, here you have CH3. So proton is you are getting double bond here, and here you will get O minus. Next what you have? See, you have Me3SiCl, so O minus will attack on the silicon center, and chlorine will leave from here, right? Chlorine will leave from here. So what you are getting? So you have a double bond here you have CH3, and here you are getting OSI-Me3. Up to this clear? Any doubt? So triethylamine is abstracting the proton from here, you are getting thermodynamically controlled enolate. Okay, then O minus is attacking on the silicon center, because this is also hard, silicon center is also hard, so you are getting OSI-Me3. This thing is clear?
Yes.
Yes, sir.
Clear, right? Now with this thing they have mentioned another reagent. So this reagent they have mentioned, you have cyclohexanone. Okay, cyclohexanone in presence of TiCl4. Yeah, this thing. So yeah, do it. Tell me what can happen. Do it. And this thing na, this SiMe3, so this is basically actually known as your silyl anol ether. This particular intermediate is basically your silyl anol ether. Okay, so now this silyl anol ether is reacting with this thing. Do it. Try to do it. চলছে না বল, আমারটা কিন্তু চলে না, আমি দেখিয়েছি। আচ্ছা, গান লাগাচ্ছি আর মাথা খারাপ।
অনেকদিন শুনি জিওটা কিছু জায়গাতে চলে, বড় বড় সিটিতে জিওটা চলে, কিন্তু যেটা তোমার এয়ারটেল
সেটাই তো দেখছি আমি।
ওই জন্য আমি এয়ারটেল মাকেও এয়ারটেল করাই না, কারণ জিওটা শুধু খাদাড়াতেই চলে, যখন খাদাড়া থাকতে জিও, এয়ারটেল তোমার খাদাড়াতেও চলবে, গায়েও চলবে, তুমি জঙ্গলের মাঝেও যাও জঙ্গলেও চলবে। এয়ারটেলের মারাত্মক টাওয়ার দেয়, আমাদের ওইখানে কাতিপুরে জঙ্গলের মাঝখানেও টাওয়ার ছিল এয়ারটেল। মাথা খারাপ, এরাই গেছিলাম জঙ্গলে, মানে ঘুরতে গেছিলাম তো ইয়া সাপ খুঁজতে, সাপ খুঁজতে একটু ওইখানে একবার ইয়াতে রাসাল ভাইপার পাই গেছিলাম, মানে রাসাল ভাইপারে খুঁজে গেছিলাম আর পিছনে, যে রাসাল ভাইপার পাই না ওইখানে, দিয়ে আস্তে আস্তে তখন সন্ধ্যা হয়ে গেছিল, শুয়োর জঙ্গলি শুয়োর পাইছিলাম, ঠিক কি গাছে উঠে দিয়েছিলাম, আর জঙ্গলি শুয়োরের ঝুঁক বিরাট ভয়ঙ্কর, যদি একটাও ভয়ঙ্কর, একটা জঙ্গলি শুয়োর যদি ইয়ার মধ্যে মানুষ মারি দিবে, তাহলে সামনেটা 10-20টা জঙ্গলি শুয়োর, আমি তো আমার বন্ধুটাও আগে আগে যাচ্ছে, আমি পেছনে কানে হেডফোন লাগাই একদম ভোজপুরি গান চলতে চলতে আমি যাচ্ছি, আমি দেখছি দাঁড়ায় দিচ্ছি, আর আমি চুপচাপ একদম আচমকা কোনো শব্দ না করে দাঁড়াই, আর আমি যদি পাতায় ধুম শব্দ করতে গান করতে বা এই ঝোড়টা, আমরা এখানে রাস্তা ঝোড়ের ওই পাশেই 10-20টা ঝুঁট পুরো একদম, আর আমি এরকম পাতায় শব্দ করতে করতে যাচ্ছি, উবার ফাটছি, আমি একটু একটু স্টেশনে উবার ফাটছি, যে আমাকে ইশারা করছে, আমি দেখলাম কি হয়েছিল, হেডফোনটা খুলতে আমি বুঝতে শব্দ পাইছি, যে আমারও বুক শুকাই গেছে, উবার যখন আমি বলে আমি তো প্রথম শুনতে পাইনি তখন,
দাঁড়া দাঁড়া, এটা পড়াই দিতে শুরু, দাঁড়া
বিরাট কিছু হয়েছিল সেইবার,
দাঁড়া।
ম্যান ফাটাই দিয়ে এইখানটা আমার কার্বন পেন্সিল এতটা ছিঁড়ে গিয়েছে, যখন জঙ্গল থেকে বেরাচ্ছি তখন দেখি এইখানে ছিঁড়ে গিয়েছে, এইখানটা কাটি গিয়েছে, বিরাট অবস্থা বললি, আর ঘরে ঢুকেছি সেদিন।
দাঁড়া।
আগের ফোনটা থেকে ভিডিওগুলো দেখাইতো, নতুন ফোনে নাই কিছু, আগের ফোনটা থাকলে সব ভিডিওগুলো দেখাই।
Okay, fine. So what you are getting here?
মেসেজ আসছে আমার সাথে কিছু,
What you are getting? So see this oxygen silicon bond, if you have, so silicon is what? Silicon is positively charged. Silicon is positively charged, oxygen is negatively charged, right? So what will happen? This O minus, you can think like this oxygen silicon bond is actually a polar bond. So O minus is actually gives back its electron, okay, and this double bond will now attack on the electrophilic carbon, and this double bond O will break. So what we are getting? See, so here basically you will get double bond O, okay, and this carbon center is attaching with this carbon center, so you can draw a bond like this, okay. Now suppose here you are getting 1 2 3 4 5 6, and here you will get what? OH. Basically you will get O minus, initially you will get O minus, but you will get ultimately OH, and here you have methyl group. Now can you tell me what is the role of this TiCl4? Why we are adding this TiCl4 with this cyclohexanone? What is the role of this TiCl4? Am I audible?
Yes.
What is the role of TiCl4?
Does it increase the electrophilicity?
So basically it is a Lewis acid. This TiCl4 is a Lewis acid, and if you have a Lewis acid, so that means what? This oxygen is donating the lone pairs to this vacant d orbital of titanium, okay, because you can what is the oxidation state of titanium here? +4, right? So 3d0. So you have vacant d orbital on titanium, so oxygen is basically donating the lone pairs on titanium, and you will get a thing like this, TiCl4. So oxygen will be positively charged and this titanium is negatively charged, so basically it is increasing the electrophilicity of this carbon center so that it can easily attack on this carbon center, okay. So to get a higher yield of this compound we are doing this, okay. And one thing, sometimes they ask, okay, OSIME3 generally does not break like this, so how it breaks? So oxygen has lone pair, so basically oxygen will gives back its lone pairs and then it will attack here, okay. So it will be like this, but yeah, you can show like that, you can remember, because oxygen silicon bond is a polar bond. Okay, so you can clip like this and then you can show the mechanism. It will be easy to understand for your understanding. Clear? Any doubt? Any doubt?
Yes, sir.
Sir, is there possibility like McMurray coupling here?
What possibility of
If McMurray coupling.
megameric coupling with what? Okay, yeah, here you are asking TiCl3. Megameric coupling is also possible, but magmatic coupling is also possible, but I think there will be a specific temperature, so that they have not mentioned anything about the other conditions, because TiCl3 is you are using, that is fine, but we have some solvent also, even temperature also, so that they are not specifically mentioned. And when you have this kind of system, suppose you have a enolate system and then you have other electrophilic system, so that time you can do addition. Okay, that time you can do addition. But if you have only this compound, ketone compound, and then you are giving titanium chloride, hitting those things, that time you can do your McMurray coupling. Okay.
Yes.
Hmm.
Uh,
Okay.
sir, it is
uh,
formed the
uh, uh,
bridged compounds. Uh, is there any possibility to form that spiro compound, sir? The reason why I'm asking is uh, the double bond is attacking the carbonyl compound.
uh,
Then it will form the spiro compound, sir.
here you are asking about spiro.
Yes, sir. Yes, sir.
But
Yes, sir.
spiro is not possible here, na? Like from this condition you are asking.
Yes, sir. How the single bond is formed, sir?
This single bond, how it is forming?
Yes, sir.
No, it is simple, na? See, so suppose you have O minus and here you have SiMe3, right? So what I told, that silicon is metal, so it will be positively charged, oxygen is negatively charged. So if it backs its electron density, this double bond is attacking here, so that means this carbon is attacking here, na? This carbon bond. So that is why the single bond is forming.
Okay, sir.
Clear? Basically you will get a
Yes,
thing
sir.
like this. You will get a thing like this. You have oxygen here, then you have hydrogen, then you have TiCl4. Directly you will not get this thing. Okay, positive, negative, then TiCl4 will leave from here, because it's a Lewis acid kind of thing. So you will get OH here, and this is the thing. Okay.
Yes, sir.
Spiro you will not get from here. Okay, now suppose you have this thing you guys do. Okay, this thing you guys try to do. So here you have double bond O, here you have methyl. Okay, then here I am giving what? LDA. Okay, THF minus 78 degree centigrade. Okay, second thing you are giving here Me3SiCl, which is very easy. Up to that you can do easily. Okay, third reagent they have mentioned here, butyl lithium in presence of THF. Okay, butyl lithium in presence of THF. Okay, first of all do up to that, then we will do further. Okay, first of all do up to that.
क्या कर रहे हैं?
একটু হয়ে গেছে তোটা। So what will happen? LDA will abstract the, because you have minus 78 degree, minus 78 degree. So what will happen? Thermodynamic or kinetic?
Kinetically
So
controlled, sir.
kinetically controlled. So LDA will abstract the proton from this side, and you are getting annulate from here, right? So what I am getting, here you have methyl group, this side you have double bond, here you have O minus, next you have SiMe3Cl. So you know what will happen, O minus will attack on the silicon center, so I am writing directly, you will get OSiMe3. But now tell me the third reagent, what it will do. Butyl lithium THF, what it will do. So butyl lithium means what? It's basically a base, but if you see here, you have not that much acidic proton available, right? So what can happen? What can happen? This is a base, okay? This butyl lithium is a bulky base, so generally it abstracts proton, but here you do not have that much acidic proton, because if you see, only here you have proton and here this you have no proton, because only this side, these are not that much acidic proton. So what can happen? So sometimes they does not use the fluoride source. Suppose if I use here this reagent, tertiary butyl ammonium fluoride, that time what will happen? Tertiary butyl,
Silicon fluoride.
silicon fluorine bond will form. So basically what is happening, F minus is attacking on the silicon center, this bond breaks, right? So similarly
Yes,
here
sir.
also if you see, here also if you have butyl minus and lithium plus, so butyl minus is actually attacking on the silicon bond, okay, and this bond breaks. Now how it is attacking? So basically butyl minus is donating the electrons on the vacant d orbital of silicon, and this bond breaks. So that means you are deprotecting the silyling agent, okay, you are deprotecting that reagent, okay. So what you will get? You will get here O minus, okay, O minus. So now it is free, okay, you are getting it free. Now suppose here I am using this, what we are using, cyclohexanone, right? Cyclohexanone, okay, and number 2 is your H3O plus, just hydrolysis step. Tell me what will happen? What will happen?
The two rings will attach.
So O minus, again it will back its electron density, this carbon will attack on the carbonyl carbon, this bond will break. So basically again what you are getting, okay, I have to draw this side na. So how can I draw? Okay, just a minute. So here you will get double bond O, here you have methyl, okay. Now this carbon is attacking on this carbon, so that means this carbon is directly attaching with this 6 membered ring. So 1 2 3 4 5 6. So what I am getting? I am getting here OH, okay, fine, clear? Kaveri, clear?
Yes, sir.
Okay. So these all the reactions are basically your carbon-carbon bond formation reaction. These are your carbon-carbon bond formation reaction. If you do organic synthesis, you will do that time. Um, so here you have first they are using base. Okay. Second, they have this reagent. PPH3 plus, and here you have what, CO280. Okay, so now do it. Okay, try to solve it, then tell me what you are getting. Try to solve it. So what will happen, initially base will abstract the proton from here. Okay, base will abstract the proton from here. So what I am getting here, so here you have double bond O, here also you have double bond O, and you are getting negative charge on nitrogen, right? Now next what you have a three membered ring. So if you have a three membered ring, I am writing it again here. So suppose here you have what, PPH3 plus, and here you have CO280. So what will happen, this negative charge will attack, okay, on this carbon, and this three membered ring is now opened. Okay, this three membered ring is now opened. So what you will get, so here I have nitrogen, here you have double bond O, it is attacking on this carbon. So this is basically one CH2. So I can write down like this, CH2. Then what you have next, you have again CH2. So write it down again, CH2. Next, so CH2, then you have this tertiary center. So draw it. So what I have, so basically here I have CO280. Okay, this side you have PPH3 plus, and see this bond breaks to here, so that means the electrons are coming to this center adjacent to your PPH3. So adjacent to PPH3 you will get a negative charge. Okay, now what can happen if you have this compound, what can happen, so this negative charge will attack on the carbonyl carbon, this bond will break. Okay, this is your intramolecular reaction type. Okay, so what I am getting, so here you have nitrogen. Okay, double bond O is there, so CH2, then again you have CH2, and next you have this carbon center. Now it is attacking here, so that means 1 2 3 4 5 membered ring you are getting again. Here you have CO280. Okay, and this side you have what, this side you have PPH3 plus, and here you are getting what, O minus. Next will be what, if you have O minus PPH3 plus, you know oxygen phosphorus bond is strong. So what will happen, oxygen phosphorus bond will form, right? So here you have nitrogen, double bond O, here also you have 1 2 3 4 5. So now let me check what I have here. So here I have CO280. Okay, and this side you have PPH3. Okay, and here you have oxygen, and they are making a bond. So this is basically a Rutig reaction type. then what will happen? This carbon oxygen bond will break and this carbon phosphorus bond will also break. So Wittig reaction is happening here, and ultimately what you are getting? Ultimately you are getting, so here you have double bond O. So 1 2 3 4 5. So here you have a double bond, and what you have here, this side you have CO2 80. Clear? Any doubt? Any doubt?
Clear.
Clear, right? Clear? Any doubt? Okay, so
Yes, sir.
two things I am giving you homework. Okay, so you just practice it. Tomorrow I will check. Okay, maybe tomorrow also I will take the organic class, because I want to finish this enolate thing. Then I will move to inorganic or physical maybe. So one step reaction only. Okay, do it. You can do it easily basically. Fine, do it. These are the two things you have to do. Okay.
Yes, sir.
Okay. Any doubt from today's class? Any doubt you have?
No, sir. Clear, sir.
Clear, right? Sampriti, clear?
Yes, sir. Clear.
Okay, fine. Okay, so practice the organic chemistry. Okay, revise the old thing also. Your reagent chemistry, those things also revise it well. Okay, and practice it well. Okay, more and more you will practice, more you can score well in organic. Okay. Okay, fine.
Sir.
So that's it for today. We will meet tomorrow. Okay. And yeah, any doubt, just let me know. Okay. And study well. Okay. Bye. Thank you.
Thank you, sir.